Good morning. My video today is going to be a little bit different. You'll be able to hear me, but you won't be able to see me. The reason why that is this involves looking at some graphs, and so I thought that would be easier if you could actually see my screen, so you'll follow my cursor as I'm pointing at different things on the graph. Alright, so what we're going to do next is there's another thing that we can use derivatives for, and specifically the second derivative. And this is actually a topic we really haven't talked about because it's hard to see in an initial graph, but it's really easy to locate if you know a little bit about derivatives. And so I'll refer to this graph I have drawn up here in a second. So what that thing is called is concavity, and it helps kind of distinguish the different types of increasing or decreasing functions. So we've done increasing and decreasing before, and that's really easy to tell from the graph because if it's going up, it's increasing, going down, decreasing, and so on. What it means for concavity is there's two types. Concave up, which means it's increasing, but it's kind of bent upward. And then there's concave down, which is increasing or decreasing, but it's bent downward. And then concave up can also be decreasing. I forgot to say decreasing. So if you look here at this little graph I have sketched up here, you can see that it's increasing until it hits this. This would be our maximum, then it decreases for a while, and then it hits our minimum that I have pointed out here, and then it increases again. So we've done that in the past. That's easy to locate from the graph. But what we haven't done is, like I said, this concavity. So if you look at this first part of the graph, this would be considered bent down. And so even though it's increasing here and decreasing for this first little part, both of these sections are bent down. And it's kind of like around here where I put my green dot, where it switches and now the graph is bent up. So it's really hard to locate this, which we'll call point of inflection. I'll define that in a little bit, to figure out when the graph switches from being bent down to bent up. And what this really helps with is if you're ever trying to sketch out a function, if you have the most detail, this will really help you draw out the graph. So what this would ultimately lead to, and I don't know if we're going to get to this through the online stuff, but I could give you all kinds of stuff about the derivatives, and then you could sketch me the original curve without having the original function, is what this ultimately leads to. Anyway, so let's do a couple more definitions. Oh wait, I got a couple more pictures. So here, like I said, this just kind of breaks it down. So this part of the graph up here in this upper left-hand corner is showing a decreasing, that's concave up, so it's kind of bent upward. And then the second half up here in the upper right is concave up, but it's also increasing. So again, you can see kind of how it makes two halves of a minimum. That's kind of where concave up lives. Concave down on the lower left, decreasing, but it's bent downward, so it's decreasing. And then concave down and increasing is this bottom right-hand graph. So and you can kind of see that they kind of make the two halves of a minimum or maximum. That's another thing we can notice. But it doesn't always have to be a minimum or maximum, because if you look backwards, okay, you have to kind of be able to pick out, okay, where does this downward stop and where does upward begin. So that's what the second derivative will help us with. So this is called the second derivative test because we use the first derivative to help locate extrema, so those minimums and maximums that I had pointed out with the red dot we can find using the first derivative, and the second derivative helps us find concavity. So like I said, if I give you enough information, you should be able to do a nice sketch of the curve if you didn't have the original function. So what we need to do is look at the graph of the second derivative. What concavity is based off of positive and negative of the second derivative. So if we look at the graph of the second derivative, if it is positive, that's what this part means, f double prime of x is greater than 0, so it's positive, that means that the graph would be concave up over that interval. So concavity is over an interval. So you have, usually it's like intervals we've done in the past, where it'll start with negative infinity and with positive infinity, and it might have several different parts where it might be positive. So you might have a couple of different intervals of concave up. So then, in order for it to be concave down is the other choice. Concave down would be where it's negative, so it's where it's below the x-axis. So if you're looking at the graph, if it's positive, that means it's going to be above the x-axis. If it's negative, it'll be below the x-axis. So wherever the second derivative is negative, we list that as concave down. Now, like I said, you can have multiple intervals of each one. It's actually possible for your entire graph to be above the x-axis. So that means it would be concave up the entire time. It's also possible for your graph to be below the x-axis the entire time. In that case, it would be concave down. So there is possibilities of just having one type of concavity. So if your graph's always bent upward, like one thing I can think of is if it's a parabola, if it's pointing upward, that's always concave up. Same thing if you flip that upside down, always concave down. So there are some graphs that have just one type of concavity, but they should have some type of concavity. Now, the other option is if it's zero. The zero is where that point of inflection comes in. And so that's the new phrase, I mentioned it earlier. So where it's zero, where it crosses the x-axis, that's the point of inflection, and that's where it changes shape. So what we can do first is identify the point of inflection, and that'll look very similar to what we did with the last section with identifying extrema. We'll find the second derivative, set it equal to 0. That'll give us the point of inflection, so we'll know where that changes. And then after that, we will then look at the graph so we can look at the intervals of concavity. So those are my two directions. Now I have it all typed out over here, but I want to show you step by step. So that's why I got this blue outlined box here to cover some of the stuff up. So our directions are, we're going to find the point of inflection. So like I said, that's going to look very similar to when we were finding extrema in the last section. We'll set that equal, or find the second derivative, set it equal to 0, solve for x. A lot of times there's just one point of inflection, but sometimes your graph does change inflection a couple times. That happens, you know, more than one point of inflection. And then the other thing we're going to do is determine concavity, and that's where we're going to look at the graph. If the graph of the second derivative is above the x-axis, it's concave up. If the graph of the second derivative is below the x-axis, it's concave down. So here's our first equation. So our first couple steps are to take some derivatives. So we have to take the first derivative, which I have here, which we actually aren't going to do anything with this. This is what, if I were doing the last section, I could set it equal to 0 and find my my extrema. But what I'm worried about is the second derivative. So that's what I have down here. So we have the 12x plus 18. Okay. So my first step is to find the point of inflection. So I'm going to take the second derivative and set it equal to 0. Cover it up as much as I can. And so this one's a pretty quick solve. We'll just have to add 18 and then divide by 12. So our point of inflection will be 18 over 12, or if we simplify that a little bit, is negative 3 over 2. So that's our point of inflection. And that's hard to type out all the time, so I just abbreviate it to POI. So point of inflection, POI. Point of inflection. So that's where the graph would change shape. So now what we're going to look at is we're going to take the second derivative. We're not worried about the other graphs. We're going to take this second derivative and we're going to put it into our graphing calculator. Let me pull over to Decimus real quick. I just need to type 12x plus 18. So there's our graph. And like I said, most of the time when we're looking at concavity, we'll have very simple...
The time is 9:04 a.m.
Thank you, Alexa. Sorry that got in there. Bye. Oh, technology. Alright, so if you look here, here's our point of inflection, negative 3 over 2, which is negative 1.5. So that's our negative 1.5 or negative 3 over 2. That was our point of inflection where it crosses the x-axis. So we already identified that. So what I need to look at is what's happening after that point and before that point. So this one, so as we follow the graph, okay, notice it's below the x-axis, hits that point of inflection, and then goes above the x-axis. So what we're going to identify is that this, click and drag, is that this portion that's below the x-axis, is concave down, and this part that's above the x-axis is concave up. So since we read a graph like we read a book, we're going to start with the concave down part, because that's where if you keep zooming out, so it starts from here. So wherever the graph starts being some sort of concavity, we're going to say negative infinity. So from negative infinity up until the point of inflection is concave down, and then after the point of inflection to positive infinity is concave up. So that's what I have listed over here. And I still use that negative 3.5. If you want to use negative 1.5, that's fine. So it was concave down from negative infinity to negative 1.5, and then concave up from negative 1.5 to infinity. So that point of inflection really does dictate our concavity. So once you find that, you're going to use that in your intervals. And if you have multiple points of inflection, then you'll just have multiple intervals of concavity. So again, if we look back at the graph, concave down from negative infinity up to negative 1.5, concave up from negative 1.5 to positive infinity. Alright, so that's our first example. So again, find the second derivative. So you don't have to do anything with the first derivative. Find the second derivative, set it equal to 0, solve for x. So we have our point of inflection, and that point of inflection helps us with our concavity. Hop over to the graph. Again, you always start from negative infinity into positive infinity, where actually it's x values technically. So all the way left to all the way right, just like we did with increasing and decreasing way back when. So it's, since this is below the x-axis, it's concave down from negative infinity to negative 1.5, and then it's concave up after it goes above the x-axis, and so on. Okay, try not to repeat myself too much. So there's the first one. So again, since the process is kind of similar to what we did before, I'm trying not to do a ton of examples, but I do have 4 total examples, so we're going to do 3 more. So here's our equation. So again, find the first derivative. We don't need to worry about anything with that. Find the second. So I got 12x squared plus 12. We're going to set that equal to 0. There's a couple ways to do this. The way I like to do it is still tight, kind of with factoring with the x squared. I did the common monomial from here because they both have a 12. So I pulled that 12 out to make my equation a little bit simpler, kind of like I did before. If you did, just go ahead and subtract 12, divide 12, and then take the square root, that's fine. You should end up with the same answer, but like I said, this will simplify the equation. So since I had a common 12, I pulled that out in front. And so then I divided that out. 12 divided by 12 is 1. 12 divided by 12 is 1. So then we have our things that we're going to set equal to 0. So again, 12, you could set that equal to 0, but that won't give you anything. So then here with our second example, or our second part, we're going to take x squared plus 1, set that equal to 0 to find our point of inflection. So I subtracted 1 and then took the square root. So then there's one thing you have to remember whenever you take the square root, we always include plus and minus. Now this one, when I subtract 1, notice it's negative. What happens when you take the square root of a negative? There's I. Okay? So it's throwing back in some of our square root stuff from way back when we first talked about that in Algebra 2. So whenever you take the square root, it's always positive and negative, that solution. So that's why I have my plus and minus here. The square root of 1 is 1. And then it has an I because it's negative. So those are my points of inflection. So that's our points of interest. Now I want to point out sometimes when I shows up, that's going to affect our concavity a little bit. Okay? Because that's not a real solution. So I don't think this graph is going to cross the x-axis because of that I. okay? If we had a regular old number, then it would cross the x-axis somewhere. So you're going to see that in our graph. So let's hop over to Desmos. Type this in. So we got 12x squared plus 12. So it's off my screen a little bit, so I'm going to zoom. So here is my graph. Notice it does not cross the x-axis, so it never changes sign. So notice this graph is always positive, so it's always above the x-axis, so it's never going to go below the x-axis. So if it's above the x-axis, that means it's concave up, and since it never changes, it's going to be concave up the entire time. So whenever something is concave up or concave down from the entire time, we just say it's concave up from negative infinity to positive infinity. So since the graph of the second derivative never changed sign, notice it's always above the x-axis. Again, it turns, but does not go below this x-axis. It's concave up the entire time, so it's concave up from negative infinity to positive infinity. You don't see that happen a lot. Most of the time, our examples are going to be like the first one, but every once in a while you'll see one that is concave up the entire time, just like that. Okay. Now on to the third example. So you're going to find the derivative. So first derivative here, 8x minus 3. Second derivative is just 8. So this is another unique one. So to find my point of inflection, I have to set this equal to 0. But does 8 equal 0 make sense? No, it does not. So it is possible for this to happen. I've kind of had two weird examples in a row. Since 8 can't equal 0, there is no point of inflection. So that means that we can still do concavity, but there is no point of inflection. And so what that's going to indicate is another one of these cases where it's going to be either concave up or concave down the entire time. So that means it's never going to cross the x-axis. So let's look at the graph. Hopefully you remember what just the graph of 8 equals. Now if I just type 8 when I'm trying to do that, it doesn't quite work. So the way I can kind of trick the graphing calculator, if you do y equals 8, we have this horizontal line, which if you remember back from our algebra 1 days, when it's just a number, it makes a horizontal line. So notice it's above the x-axis the entire time. So since it's above the x-axis the entire time, it's concave up from negative infinity to positive infinity. Now here's a thing that you can use as a helpful hint. If you want, whenever you're looking at this graph, whenever you get a second derivative that's just a single number, that means that you're going to have no point of inflection, and it's going to be concave up or concave down the entire time. Now how you can do this without having to look at the graph, since I knew this was positive 8, well positive 8 is going to be above the x-axis because it's positive, so I could have told that just from the number that I had that it was concave up the entire time. If I get a negative number here, so say it was negative 8 instead of positive 8, that means it was going to be negative, so it's going to be below the x-axis, so then I can switch it and say that it's concave down. Okay, so that's a couple helpful hints. Again, if that didn't make sense to you, that's fine. Go ahead and look at the graph. But again, the one thing with Desmos is if you just type a number, it doesn't want to read it as a graph. So you just have to type in y equals that number. And you can do that with all the equations if you want, but typically it reads it if it has an x. It's only if it doesn't have an x that it kind of trips it up a little bit. Okay, so here's example 3. So a lot of stuff will be like example 1. Just go back and review real quick. So a lot of times you'll just have one point of inflection, so you'll have an interval of each. Sometimes if your point of inflection is I, then it's concave up or concave down the entire time. If you have no point of inflection, you can still do concavity. It's just either going to be concave up or concave down the entire time. So I have one more example, and that example will be when we have more than one point of inflection. So if you just have a one point of inflection, you're just going to have an interval of each. If you have more than one point of inflection, then you have more intervals of concavity. Okay. So here's our fourth example. So again, we have to take the first derivative and then the second derivative. So we end up with 12x squared minus 16. So again, to find the point of inflection, we set that equal to 0. From here, if you want to go ahead and add 16 and then divide by 12, that's fine, and then take the square root, that's also okay. But what I did is just to kind of make it more simple, since we know a little bit about factoring. So I took out the common 4, so I took out the GCF. Again, then the 4 would go away, so I'm working with a little bit smaller numbers. So they're going to add the 4, and then divide by 3. So then that's going to be 4/3. And then to get rid of the square, I have to take the square root. So I'm going to take the square root of both sides. So when I took the square root of 4/3, you can either leave it as the square root of 4/3, or if you want to go ahead and solve that out, the square root of 4/3 is 1.15. So if you want to type it that way, I think I just left it as square root of 4/3. Now remember, what do we always have to have when we take the square root? Positive and negative that square root. So actually we're going to have two answers. So it's going to be positive 1.15 and negative 1.15. We do not have to have an I with this one because 4/3 is not negative. So if you look at my answer, we have positive, negative, the square root of 4/3. Like I said, if you want to take the square root of 4/3, that's fine. It's 1.15. So those are my points of inflection. Like I said, technically there's 2. I wrote it as 1 with the plus and minus there, but it is positive square root of 4/3 and negative square root of 4/3. So now let's look at the graph. And I'm going to type in the original equation, so 12x squared minus 16. So whatever you type in should be before you do any of the solving. So here's my graph. It looks kind of weird at first. So if you zoom out a little bit, it is a parabola. Okay, so it goes down, it hits this point, which, like I said, that's negative 1.15, which is the square root of 4/3. And then it goes down a little bit. We don't need to worry about this point. And then it turns and goes back up, and then crosses again at positive 1.15. So again, that's that's the square root of 4/3, that point of inflection that we found. But because it's above the x-axis to start with, then it's below the x-axis for a little bit, and then it comes back above. There's actually going to be 2 intervals of concave up. So this first part of the graph is concave up because it's above the x-axis. The second part of the graph is concave up because it's above the x-axis, or third part of the graph, sorry. The second part, this middle part here, is below the x-axis, so it's going to be concave down. So there's going to be 3 intervals. So concave up from negative infinity to negative 1.15. Concave down from negative 1.5 to positive 1.15. And then it's concave up again from 1.15 up to positive infinity. So again, technically we're reading it as x values, so we start from negative infinity, work to this point, then go down, work to this point, and then it's positive infinity for the rest of the time. Okay? So concave up, concave down, concave up again. So I'll write that as my intervals. So there's 2 intervals of concave up, and just like we did before with increasing and decreasing, I just said concave up and I listed both intervals. So it's concave up from negative infinity to negative 1.155, and concave up again from 1.155 to infinity, and then it's concave down from negative 1.155 to positive 1.155, which again, that this value is just the square root of 4/3 done out. So go back and review quick. So what we're doing now is working with the second derivative. So find the second derivative, set it equal to 0, find the point of inflection, then look at the graph for the concavity. So this graph had 1 point of inflection, so there was an interval of concavity for each. This graph had a point of inflection that was imaginary. So when that happens, it's going to be an interval of one or the other, from negative infinity to positive infinity. This graph had no point of inflection because you couldn't solve the second derivative because it was just a number. But again, you can still find concavity, so it's either concave up or concave down, depending on the sign of the number. So if it's positive, again, it's concave up, negative, concave down. And then this one had 2 points of inflection when we solve it. Positive square root of 4/3 and negative square root of 4/3. So when you look at that, there's actually 3 intervals of concavity because it switches sign twice. Well, I hope this makes sense. Again, sorry you can't see me today, but I thought this might work better to show you the graphs. So if you have any more questions, please let me know. I'll have a little assignment for you to do with 4 or 5 questions over this topic. Again, hopefully everybody's staying safe and healthy. Hope to see you soon. Bye.